I think that for sure is nice. Well, I think that uh, we are live. Yes, so good morning from the Netherlands. Here it's 11 in the morning, and good afternoon and good evening everyone. I'm Dr. Gemma Casolino from Tilburg University and Geronimo Saccario of Data Science, and I will be the session chair for this incredible session about machine learning with and for software engineering part 2. So today we have very nice papers about, of course, machine learning, 5 of them, and all the presenters are here, and I think that this session will be very funny. So how it will work the session. So we have 5 papers. So the first 25 minutes will be dedicated to the presentation of our presenters, and then we will have a broad discussion all together. But please, also during the presentation, consider to start writing your question in the chat, or also when we will start the discussion, consider to just unmute yourself. This year, Meetspace is really interactive, so we need to, keep this opportunity. So, okay, so let's start with the first paper. So Nadia will present the first paper, and is about lesson learned on reproducibility machine learning based Android malware detection. So please, Nadia, the stage is yours.
Thank you. I think so.
Yes.
Thank you. So, hello everyone. I'm Nadia Daoudi, a doctoral researcher at SMT at the University of Luxembourg. And today I will present our paper, Lessons Learned on Reproducibility in Machine Learning-Based Android Malware Detection. This work has been conducted together with Dr. Kevin Alex, Professor Tegavin Debisyande, and Professor Jack Lang. So as you know, Android is very popular among mobile users since it has maintained the highest market share over the last 10 years. But Android is also a victim of its own success since attackers target Android to spread their malicious applications. To tackle the spread of Android malware, many approaches have been proposed in the literature leveraging machine learning techniques. But malware still finds its way to mobile users. In our work, we aim to assess published work to see why malware is still spreading despite the massive work published in the literature. In this paper, we thoroughly assess the reproducibility of published work, since the reproducibility is an important criteria for acknowledging a research contribution. So in our paper, we conduct a reproduction study, which means that we are a different team that tries to use the same experimental setup of original approaches. And here I want to mention that this work should not be seen as a criticism of the reproduced approaches. Actually, being selected in our study means that these approaches already care about open science, since they make some or part of their artifacts publicly available. To conduct a reproduction study, we need to collect the dataset, extract the features, embed them in vectors, and then train the machine learning algorithm for declassification. How we have selected our reproduction subjects. So we have considered 16 major venues in software engineering, security, and machine learning, and papers that have been published between 2009 and 2019. And after applying our selection criterion, we have ended up with 5 papers that satisfied the minimum criteria for their production attempt. These papers are Dribin, Mamadroid, RevealDroid, DroidCat, and Mason. So our study has showed that only 1 out of 5 approaches can be reproduced. Actually, the time doesn't allow to go through all the problems we have faced during our production study. So it's not about executing the code and writing down the results. It involves collecting data sets from different sources, which can be really challenging. And even when the code is provided, it needs to be reviewed, completed, debugged, and sometimes even corrected. And that involves a massive guesswork and code rework. Also, our study has raised the problem of the absence of a systematic method for deciding about the success or failure of a reproduction study. And also, when an approach is not reproducible, it cannot undergo a refutability check. So to conclude, in our paper, we describe our production journey of 5 approaches on machine learning-based Android malware detection. And with this work, we hope that we all learn lessons from our production study and invest more in making our work reproducible. Thank you.
Thanks, Nadia, for your presentation. So now we can move to the second presentation. I want to remember that we will have later the discussion with the question. So let's move to the second paper, and in particular, Amrita Saha will present her paper about money root cause knowledge from cloud service incident investigation for AI ops. So please, Amrita.
Thanks, Gemma. Yeah. So I'll be presenting our work on mining root cause knowledge from cloud service incident investigations for AI ops, which is a work done in Salesforce Research Asia. The incident root cause analysis life cycle follows like this. We first do incident detection, and then through various analysis, we do symptom detection, followed by investigation by the site reliability team, which triages the incident and finds an immediate resolution, and then RC investigation by service owners to find the root cause. This entire process is documented in long unstructured documents known as PRBs, or problem review board data, which you see on the right-hand side. And this is a generic source of rich RC information, which is available in all incident management systems. So the main research question in our work was, can AI assist ongoing incident analysis based on the past investigation data in the PRBs? We achieve to do this by extracting and mining relevant RC information from the PRB data and reusing this knowledge to quickly resolve repeating incidents. So our primary contribution was to build this incident causation analysis engine, which we call ICA, over this PRB data. And it consists of first a neural information extraction system to extract RCA information from the unstructured PRBs. Second, neural knowledge mining to aggregate incident information into a causal knowledge graph. And then we use ICA for neural incident search over PRB repository to find similar past incidents, and do a retrieval-based root cause analysis to detect likely root causes and resolutions given an incident symptom. So the incident causation analysis pipeline goes as this. We start with the unstructured PRB documents. We do very high-level structure parsing, which gives the subject, the investigation details, and then the RCA details in terms of what was the immediate resolution and root cause. And then we have a neural information extraction module based on pre-trained language models like BERT and others. And it does various things. One is like key topic extraction, summary extraction, symptom and root cause resolution extraction. And all of the extracted information along with the original unstructured document is now put into a neural search index. It's based on Roberta-based embeddings of these documents. And this serves the neural incident search. So now, given a query like high latency, high pod CPU, we can now give out the search results in form of structured PRB documents, where each PRB has the extracted symptoms, the key topic, summary, root cause, and the resolutions in form of short topics. We also have another module called the neural knowledge mining, which takes the extracted information and builds a causal knowledge graph out of it. So with this causal knowledge graph and the neural incident search, we can together serve something called retrieval-based root cause analysis. So what it does is, given a query symptom like high latency, high pod CPU, it can now suggest what are the possible resolutions or what are the possible root causes, and also show the part of the causal knowledge subgraph which is relevant to the given query. So for example, for this query like high latency, high pod CPU, it detected that customer-induced SQL execution load is one of the possible root causes. So one of the main challenges of this was ICA, all of the components of ICA were unsupervised. We didn't have any particular supervision of the kind of extraction, information extraction or the root cause analysis. So we did this kind of evaluation where for different modules, we have different types of evaluation. For the neural information extraction, we did human evaluation of around 300 to 1200 instances. And we showed that around 80 to 95% of the extracted topics and summaries were really well formed and informative. And also 70 to 80% of the extracted root causes and resolutions actually match the expert human annotations. Then for the neural incident search, we did a quantitative benchmarking over 2000 PRB records coming from real incidents happening in Salesforce. And we saw that the average overlap between the target and the top 10 retrieved PRB documents is around 30 to 35 blue points, where blue is the standard text similarity metric. And we even achieved 2 to 3% improvement over the traditional non-neural search. And for the retrieval-based RCA, if we use the neural incident search engine alone, then the root cause and resolution prediction given the symptom achieves a blue score of 29 between the true and the predicted one. And if we further use the causal knowledge graph on top of this incident search results, we can further improve the root cause and resolution prediction by further 11 to 15 points. And we also did inspection of 50 real incidents post-deployment of our ICA in Salesforce. And we saw that 56% of them had at least one of the top 3 predicted root causes, which matched the true root cause detected by the site reliability team who were actually investigating the incidents. So this is the highlights of our work. Thank you.
Thank you, Amrita, for your presentation. So let's move to the third paper presentation. And so in particular, then Susan will present the paper that is about improving machine translation system via isotopic replacement. So please, the stage is yours.
Yeah, thanks. Can you see my screen?
Yes.
Yeah, thanks. Hello, everyone. I'm Zhe Yusheng from Peking University, and this is our paper, Improving Machine Translation Systems via Isotopic Replacement. Machine translation is able to translate between thousands of pairs of languages effectively in real time. The tools such as Google Translate and Bing Translator are widely used in people's daily life. Such machine translation systems are not perfect, and the user's experience have a different character from those on traditional non-machine learning-based software systems. Recently, quite a few approaches have been proposed for testing machine translation systems. To test this system, a promising trend among those approaches is to use word replacement. For example, given the sentence, women do good research in computer science, a testing approach transfer can generate an input sentence by replacing the word woman with a similar word man. This input is further paired with the original sentence as test input. Then the testing approach feeds those two sentences to the machine translation. Since there is only one word is changed in those sentences, their translations ought to be similar to each other. In this example, there should be only one word differences between those two translations. However, if the translations are not similar to each other, the testing approach reports it as an inconsistency bug. Those approaches are good. However, precise control of the impact of word replacement is in those word replacement-based approaches is still difficult due to the fuzzy semantics of natural language words. For example, the word great in this sentence is not suitable to be replaced by the word good. To tackle this difficulty, we propose a novel word replacement-based approach called CAT to machine translation testing. Given a sentence in the thought In the source language, CAT performs isotopic replacement to generate new sentences. And the goal of the isotopic replacement is to control the impact of the word replacement. To realize this isotopic replacement, we first conduct context-aware word replacement, which replaces a word within a sentence with another word that is also suitable for the context. Then we calculate the context-aware semantic similarity between the original word and the replaced word. Use this similarity to discard the word replacement that influences the semantics. Following a testing and repair approach, trans-repair, CAT can also test and further repair the inconsistency bugs. This is the overview of our approach. In this paper, we focus on 4 research questions on the effectiveness of test input generation, bug detection, bug repair, and the efficiency. We conducted experiments on 2 machine learning translators, Transformer and Google Translate. Since CAT follows trans-repair, we select trans-repair as the baseline. For the effectiveness of text generation, for each sentence in our dataset, we generate text input with CAT and trans-repair, and we found that CAT generates nearly 10,000 text input, while trans-repair only generates 5,000 text input. For bug detection, CAT detects 129% more bugs than trans-repair. And for bug repair, CAT repairs twice more bugs than trans-repair. For efficiency, CAT is significantly more efficient than trans-repair in mutant generation and bug detection, and has a comparable efficiency with trans-repair in bug repair. To conclude, we propose CAT, an isotopic replacement-based approach to improving machine translation, and the experimental results on Google Translate and the Transformer show that CAT performs better than trans-repair. Yeah, that's all. Thanks for listening.
Thanks, Susan, for your presentation. So now we will move to the 4th paper, so the first presentation given by Hong Kang. So he will talk about detecting false alarm from automatic static analysis tools. How far are we? Let's see the answer.
Right. So thanks for the introduction. So now I'll talk about our work. And the context of our work are the warnings produced by static analyzers, such as FindBugs. Because there are no guarantees that the warnings produced from these tools are real bugs, warnings could either be actionable warnings or could be false alarms. One line of research has aimed to put a machine learning classifier in between the warnings and the developers. If the classifier predicts that a warning is a false alarm, then it is not presented to the developer. And by doing so, this would save a developer a lot of time and effort. So in the literature, many different features have been proposed, and a prior work identified the most important features out of over 100 features from the literature. And these features are known as the golden features. And then subsequently, another group of researchers found that the use of the golden features would achieve up to 99.5% AUC. So to construct such the data sets for an experiment, we would need a training data set and a testing data set. So to obtain training data, we could identify one revision of a project as a training revision in which warnings would be collected from. So we would collect warnings, compute the features, and obtain the labels for each warning. And then this is the training data set that a classifier can be trained with. And after training a classifier, we could then repeat the same procedure to obtain a data set that is used for testing the classifier. So to determine the ground truth label of a warning, prior work proposed the use of a heuristic that essentially compares the warnings at a given revision, say the training revision, against the warnings at the reference revision. An open warning refers to a warning that is present at a given revision and is still present at the reference revision. And a closed warning refers to a warning that was present at the training revision, but is no longer present at the reference revision, even though the source file is still present. Prior work assumes that open warnings are false alarms and closed warnings are actionable warnings. So one interesting class of features among the golden features are the warning context features. These features essentially captures the proportion of actionable warnings within a given context, such as a method or a file. So the intuition here is that if developers has historically fixed warnings related to a given method, then if in the future, if we see warnings related to this method, then developers may be more likely to fix these warnings. However, in our analysis of the data, we find that there's an issue of data leakage when computing the proportion of actionable warnings. To determine the proportion of actionable warnings, we will need to know the number of actionable warnings within the context, and to determine if a warning is actionable, we would do so by comparing against the reference revision. So if a warning was reported at a given revision and it's no longer reported at the reference revision, then the warning is determined to be actionable. So this introduces a problem because this was the same procedure that was used to determine the ground truth label of the warning, and this leaks the ground truth label into the features. And also this is unrealistic because in order to compute these features, we would need to know the status of the warnings in the future. And this information would not be available if we were to use this tool in practice. So we also find issues of data duplication. And then after we address the issues and re-implementing the warning context features, we find that F1 drops from 0.88 to 0.38. So in other words, we see that the strong experimental results stem from very subtle issues of data leakage and data duplication. So these issues were hard to detect, but they have a significant impact. Next, we also analyze the heuristic used to determine the ground truth labels. So the heuristic assumes that close warnings are actionable. However, after two of the authors of the paper manually annotated the close warnings, we find that many close warnings were not necessarily actionable, and many of them were only closed incidentally. So in other words, the code was closed, but the code was changed for reasons that were unrelated to the warning, and therefore we were unable to determine if the warning was actionable. Our work was a triumph of open science. We built very heavily upon the data and the scripts that were made available in packages of the prior papers. So in our experiments on the golden features, we find that they suffered from subtle issues, but had a significant impact. But we want to note that the golden features are still predictive. In our experiments, they had an AUC greater than 0.5. And we also want to stress that our work does not show that this line of work is impractical or impossible. In our work, we use only very simple classifiers, such as SVMs and k-nearest neighbors classifiers. So our work motivates the need for more work and analysis. And in our analysis of the heuristic, we find that while it enables the generation of a large data set, the labels that are derived through the heuristic do not agree with human oracles. So this implies that in future, we need to have more manually labeled data, or we need to use methods that could address the lack of labeled data if labeling data is too expensive. So that's all from me, and I'm happy to discuss this work further. Thank you for your time.
Thanks for your presentation. Very nice work. And now let's move to the last presentation of the session given by Manny Shetty. And he will talk about deep analyze, learning to localize crashes at scale.
Hey, thanks for the introduction. Yeah, today I'm Manish, and today I'll be talking about deep analyze, learning to localize crashes at scale. This is work done jointly with my colleagues at Microsoft Research. To start with some context, today when systems crash around the world, Microsoft collects crash dumps for root cause analysis and bug fixing back at Microsoft. And we would have seen this in our systems when Windows tries to send a crash dump back to Microsoft. A key component of analysis that helps with this analysis back at Microsoft is a debugger extension called Bang Analyze, which was introduced to the research community in an SOSP paper from 2009. So this debugger extension has been built and maintained for over 20 plus years and performs various kinds of automated analysis of crash dumps, such as finding the blame frame, finding the issue in the stack, and so on. But despite its success for 2 decades, there are still some challenges and that we're seeing today. First thing is that the code base has become old and obviously monolithic, and it's become hard to maintain. It's in the order of hundreds of thousands of lines, and it relies on hundreds of heuristics to analyze these different crash stacks. And newer applications that are coming up every day require some amount of custom plugins and heuristics to be rewritten again and again, and they take months to deploy these code changes. So the question that we're trying to answer in this work is, can we augment Bang Analyze with data-driven approaches which can solve some of these problems? So in this work, we try to answer that question by proposing Deep Analyze, where we leverage recent advances in deep learning and natural language processing to build a data-driven system. Specifically, we aim to predict the blame frame in a crash stack, where I define blame frame as the frame that most likely caused the crash. And thus, finding this blame frame can lead us to the root cause. So hence, like to be more specific, this particular task is quite central to the problem of crash dump analysis. Specifically, Deep Analyze has particular goals. We want to move away from manually written rules, as I said, and we want to enable this kind of analysis for newer applications and scenarios with very minimal effort and with very minimal label data as well. So our approach begins with first a large-scale study of crashes, where we analyze 362,000 crashes, and we gather some insights from this empirical analysis to guide the design of our system. Then we develop and implement Deep Analyze and evaluate it on real-world crashes. So to briefly go over our empirical analysis, like I said, we analyzed 362,000 crashes from various sources. We looked at multiple properties of crashes. For example, we looked at crash locations, that is the location in the stack where the blame frame was found. And we see that in 33% of the cases, they are deeper than the top frame, hence making it harder to identify. Next, we find that no single binary or application accounts for majority of the crashes. Therefore, any kind of application-specific heuristics or methods would not scale and solve our problem. And in the interest of time, I will go to the last insight, which is where we looked at how frequently a method is blamed in crashes. And we compute a custom metric called blame ratio, which is the ratio of the number of stacks where a method is blamed to the ratio of stacks containing that method. And what you see here is a plot of blame ratio. We find that significant fraction of methods have a blame ratio less than 1, which indicates that a method which is blamed in one stack need not always be blamed in another. And that particular decision of whether to blame or not blame a method completely depends on the context it appears in. And that context here is the other methods in the stack, which are above and below it. And I refer you to the paper for much more insights and details from an empirical study. Based on these insights, we then also take some inspiration from natural language processing to formulate the problem of blame frame prediction as a sequence prediction task. So we basically perform sequence labeling on a stack. So for more intuition on the design and why we choose this particular formulation, again, please refer to the paper. We then use a standard BiLSTM CRF based model for this sequence labeling task. To further improve performance on top of this BiLSTM CRF, we use a novel multitask learning procedure where we train the model to predict not just the blame frame, but also the high-level symptom of the crash. For example, was it a stack overflow problem? Was it zero division? Was it a null pointer error? And so on. And learning these two tasks jointly enables us to improve our performance as well as generalization of the model a lot. To evaluate Deep Analyze, we then compare against multiple heuristics as well as machine learning based baselines. And we do this comparison against 4 different applications which are quite popular from Microsoft: Edge, Excel, Word, and Outlook. And we take crashes from each of these applications, train our models on a section of the data, and test our models on data that occurs after it in a timeline. Hence, we don't have any overlap between in terms of the history of the data. So we observe that although these baselines are quite strong, Deep Analyze still combines context and complementary information using this novel multitask learning procedure and outperforms all of these baselines with an average accuracy of 90%. But the question that remains is, how do we scale this to new applications and platforms? Does this mean that I have to train a new deep analyzed model for every single application? And would that be efficient to do so? To answer that question, we propose a transfer learning approach. Here, in our empirical analysis, we found that models trained on one set of applications can be transferred to a disjoint set of applications. And we'd evaluate this hypothesis in this experiment, which we call cross-app crash localization. Here, we evaluate this by training a deep analyzed model, which we call the global model, on a global set of crashes from, let's say, X set of applications. Then we evaluate it on crashes from a completely unseen application, say Edge. We find that the global model is able to predict 80% of these unseen crashes without seeing a single edge crash during training. Moreover, we can further fine-tune that the global model to this particular application and reach, let's say, 90% accuracy with just 2,000 crash examples. So this not only creates a very scalable solution for transferring models from a global set to new applications with very minimal label data and also reach high accuracies, but it also provides more than 10x reductions in training cost during when compared to like training from scratch. So to summarize, we developed Deep Analyze using the recent advances in machine learning and NLP for crash localization. We proposed a multitask learning model for blame frame prediction and showed an effective transfer learning and fine-tuning approach for cross-application crash localization. We plan to expand to cross-platform crash localization, where we try to transfer models from Windows crashes to Linux crashes. And we also want to extend these models to other tasks that Bang Analyze performs today, such as fault localization and bucketization at the thread level. Thank you.
Thanks, Nish, for your presentation. So I think that, I invite all the presenters to unmute themselves and, also turn on the webcam, because I think that now we enter in, in the cool part, the coolest part of the session, and we will start with some questions for the author. So I will first, check in the chat, and I noticed that the first question is for Nadia, particular. So Kushal, Nadia, what are your recommendations to improve reproducibility in malware detection?
Yes, thank you for this question. So from my experience, I would say that we need to keep track and document our experiments, document how we have collected our data sets. Even that seems to be simple, but sometimes we collect data sets from different sources, from Onrozo, from different markets. But at the end, we don't really remember the sources. So we need to keep track of all of this, and also clean the repository, because some approaches I try to reproduce, like the release thousands of scripts. So at the end, you don't really know which one has been really used in the experiments, and you are in the situation that you need to guess which script. So that's problematic. And also, some machine learning experiments, they require a seed control the randomness of the results. So if we can also fix these seeds and keep track of them, that would be really helpful. So that's it.
Thanks, Nadia, for your answer. There is another question, sorry, for Zehu. So I read it. So Zensu-san has a question on semantic evaluation to generated test inputs. How do you evaluate the effectiveness of its similarity metrics?
Yeah, thanks for the question. And we computed the semantic evaluation via BERT, and to evaluate the effectiveness of this similarity metric. In the experiment, we use the human evaluation to check the effectiveness of it.
Thank you for the answer. Then we have a question for Hong. So thank you for the great talk. You mentioned find bugs to generate the initial static analysis alarm. I believe this is not a very precise static analyzer to start with. Can you comment on the impact of the precision of static analysis tools on alarm filtering approaches?
Yeah, thanks for the good question. So you're right that the experiments we worked on mainly were it was used in the prior work, and in the prior work they used Findbugs to generate the wall links. So Findbugs is a very old tool, and it's likely that using newer tools would give you a lot more performance improvements. So, but most of the features considered in the literature, they capture a different aspect of the problem. So one particular class of features they capture the process metrics. So these things would be orthogonal to the code. So while static analysis tools consider the code, a lot of these features they consider things like the processors and the developers. So it is very likely that these alarm filtering approaches would still improve on the precision of the static analysis tools. So I wonder if that answers your questions. Yeah.
I think yes. Maybe I don't know if who wrote the question on the chat. Maybe he can also unmute himself and say yes or no. So by the way, we will go on with the question. Okay, yeah, I
just wanted to say yes. Thank you for the answer.
Thank you for your question.
Yeah, and thank you for the work. Thank you for the work and identifying limitations. Just to let you know, I work at Oracle Labs, and yeah, we tried several tools from academia, and we could almost never reproduce the stellar results that are presented in many papers. So it's great to see that some people are actually drilling down and finding the root causes of why things don't work in practice so often. So thanks for that.
Right. Thanks.
Yes, indeed, it's true. It's I think that this paper, and that's now, I mean, it's clear, understand why it's has been nominated for this paper award. I think that it's clear that also if you present something that in a way wants to focus attention on something that is negative in a way, because of course the value of F measure tremendously decrease. This means that we can do also good science, not only presenting, always on the result and say, hey, everything is fine. We propose a very cool approach, so we are the best. So really, yeah, it's true. I agree. Okay, so we have another question for Zeyu. So do these metrics relate to the length? So I'm curious about your sentences about similarity metrics. Do these metrics relate to the length of sentences? If so, will small disturbation on stored sentences influence similarity severely?
Yes, this is a good question. Thank you. And the similarity is computed by BERT, and I don't think it is related to. I don't think it is related to the length of the sentence. Since I don't do the experiment, but I checked many examples generated by the word replacement and the S-topic replacement, and I think the length of the sentence is not the one of the will not influence the similarity. Yes, thank you.
Okay, thanks for your answer. So there is a question for Amrita. I think the quality of incident reports is an important factor for natural language processing techniques to work well. Do you have any suggestion for engineers about how to write high quality incident? Thanks. Really good question.
Yes. Yes, yes, it's a really important factor. And indeed, the NLP techniques won't work unless the quality of the incident reports are high quality. So, one of the things which we saw in real incident analysis, it goes on for a few days. There are various different phases in it. The incident investigation followed by the root cause analysis is done by different teams. So many of the times the documents are really quite unstructured. They have email discussions within them, cross-team communications, or other sources from which the information is coming. So one thing, one of the main points where this kind of unstructured documents are required is finding out what was the real root cause, because they will often discuss what are the possible root causes, and then maybe they'll indicate to what was the final thing which solved the problem. So it would really be helpful if these this process of documenting had some way to kind of pinpoint which was the final root cause, or which was the final way of resolving the problem. So even in Salesforce, we are trying to develop the process of documenting these investigations better by structuring the whole process. But given it's a very agile environment, maybe we won't be able to completely rely on human like human structuring the documents well enough, because it's a very long run process involving multiple teams, and also the kinds of incidents also change over time. So that's why we probably need a combination of this, like some unstructured data where NLP can be helpful, but at least if the information content has the final root cause, we have seen that NLP and some of the recent pre-trained models are very good at extracting the right information from the long documents.
So thanks, Amrita, for your answer. So I do not see any questions on the chat. I don't know if someone wants simply to unmute him or herself to ask something to the other. Otherwise, yeah, I have actually a question for Manish. I really enjoyed your presentation. I think it's really nice work, and I'm wondering whether you so you say that you perform these very large analysis of crashes, and you in a way manually investigate on them. So how was the process? Can you argue more on that? And after that, did you find, for example, that for some particular type of crashes, some particular crashes are more familiar to a particular system in Microsoft based on the domain of the system? I mean, Excel and Outlook are, came from Microsoft, but they are different. They belong in different domain. So,
Yeah, great questions, and thanks for the question. So first thing about the empirical analysis. So what we do in our analysis is basically collect the crashes and that are labeled by Bang Analyze itself. And by, again, to reiterate, what Bang Analyze is a 20-year-old tool, and so like the heuristics are quite, like it's quite verified, and everything is written by over the 20 plus years. So we, in that sense, we trust the system quite well in terms of accuracy. It's the problem that we're trying to solve here is the scale problem, because today we can't keep writing these types of rules and so on for new applications, and that's the main core of the paper. So in terms of accuracy, we believe in Bang Analyze, and that's where we get all the labels from. And the process basically goes like, we take the labeled examples from Bang Analyze, and then we'd have different kinds of research questions. In the sense, we want to understand, can we try to memorize blame frames, right? If we could just memorize blame frame, then we could just have a dictionary of blame frames and just see if it exists in the crash, and then do that. But that we find that that's not the case, because, like I said, in one crash, a blame method might be XYZ, but the same method might not be the blame frame in another. And that completely depends on the call stack. And that call stack basically is the functions that are calling it, as well as what it's calling. So the callee and caller relationships. So it's very important for whatever tool we build to actually capture that context. And that's what we kind of figured out from our empirical analysis. And yeah, and there are multiple other kinds of research questions where we try to understand what kinds of software components are crashing. For instance, we find operating systems also crash, and drivers are one very common thing.
Yeah. And also, it's really interesting to do also this kind of analysis based on the domain of software, because of course these, I mean, especially in Microsoft context, you can allocate resource in a way better if, you know, I mean, if some types of crashes, appears more in the domain of the application, like Office package in a way, you know. Yeah,
you're right. And to just add to what you said, that's exactly what happens. So if we can do this kind of prediction very accurately, what we can do is bucketize these crashes. So we can just prioritize our efforts on those crashes which are very frequent and so on. And to just briefly answer your second question, I think I kind of forgot what you asked. Could you repeat the question?
Yeah, I mean, I was about really, I mean, if you find, some interesting results based on the system that you analyze, since are different in terms of domain. I mean, I'm not talking about Excel or Microsoft or of Word, but for example, Outlook, it's, kind of different in terms of domain.
Right. So the hypothesis that we came up with, that you can actually transfer models from one application to another, it depends not actually on the methods of the application itself, it's the other methods in the stack. So if you see a stack, there's like, let's say 30% or like 50% of it is application, but there's actually a lot of underlying methods which are just common across applications, which is just your system, your Windows device manager, your device managers, or your desktop managers. And all these are kind of common across applications, irrespective of whether it's Outlook, Edge, whatever it is.
Yeah.
There's also other kinds of patterns which you can see. For example, you can have a Stack Overflow issue in Excel or in Outlook. And that issue will actually create patterns of repeating frames in a stack. That pattern you can learn either from Excel or Outlook, and that's what we want to do. So there are some common and generic patterns which you can just learn irrespective of the application.
Thanks, Manish, for your answer. Yeah, so we have a question for you again. So any reason behind choosing LSTM-based architecture instead of transformer-based?
Good question. Thanks, Amrita. And yeah, the reason is mostly in terms of like efficiency, and it's more just it's much more faster for us to deploy, even if we have to create multiple models and also train. And the other reason is that we have multiple layers, not just the LSTM in our architecture, which is, for example, the CRF layer and things like that. We found in our experiments that we found that there are certain layers which just work very well with the LSTM layer, and it's basically just a design decision there, and that's pretty much. And we're also just trying to keep the model as simple as possible. That's it.
Yeah, thanks for the answer. Yeah.
No problem.
Okay, I don't see any other question on the chat. Actually, I have a question for Nadia. So you talk about about a problem, about the fact about replication, that that an approach is reproducible and so on. During your presentation, I thought that in a way this was a cultural problem, because now, I mean, if you see in the conference, now we see that the research community now pay attention to replication, because there are artifact evaluation track. In general, now in the call for paper, program chair write that they want paper that in a way can be, reproduced and can be replicated in a way. So I'm wondering if when you did your analysis, so when you compare different kind of malware detection approach, did you find, for example, that the latest approach were more replicable in a way compared to the oldest one? This is my first question. And then my second question is, so do you agree with my, with my thought about it's a cultural problem that we have in our research community that now is changing? So now we force people to please share your data, share your science with all the community.
I totally agree with you. You are right. Actually, recently, I noticed that the community is paying more attention to the reproducibility, and especially with the artifact evaluation tracks and all these initiatives. And in my study, I attempted to reproduce 5 approaches for Android malware detection. And indeed, the latest approach, which has been published in 2019 at ISE, it was reproducible. It was really clean. The data set was really documented, the scripts and all. I really faced no issues reproducing this approach. So yes, the problem seems to be to be started to be solved. And that's very good.
Yeah, thanks.
Yeah.
Other question on the chat. I don't know if someone wants to unmute him or herself. Otherwise, I have a question for Amrita. So also based on the question that you received in the chat, it seems that we can apply artificial intelligence to derive possible root case of incident report. But according also to your discussion and your presentation, it seems really a subjective problem, because team can perform different type of incident report. I mean, the structure can be the same, but it's a really tricky problem. So what do you think about, and I mean, which are the next steps also after the work that you presented?
Yes.
That,
so,
sorry, do you think that we need to go and continue, using machine learning, artificial neural network in artificial intelligence, or maybe we need to go in a direction where we need to standardize this kind of, documentation?
Yes, it's a very good question. So I think we need to do both. Given that the kind of incidents completely change over time, and the agile process, and it will involve multiple teams discussing and doing this. It's a very iterative kind of process which we are documenting. So maybe completely standardizing it in a way that is consistent throughout is going to be hard. It may not be very practical, but still, there are efforts ongoing, even at Salesforce and in any other place as well, to make this process more structured, make the documentations easy for the knowledge to be reused. But at the same time, it may not be possible to directly reuse the knowledge from the documentations like this. So we might need to be having some NLP or some AI capability which extracts the information, or which uses the information in a way, or at least stores the information in a way which can be used by AI models as well as humans. So it needs to be a combination of both of these two things. And there's another thing is why we looked at these investigation data is that there's a lot of work on root cause analysis, looking at systems data like logs, traces, and others, but they don't have the Oracle information, what was the actual root cause for a given incident. Whereas the PRP data has somewhere hidden in those documents what was the root cause in it. So we are just trying to make that thing more structured so that we can now feed back this information into like something like a multimodal holistic root cause analysis model, which looks at all the different kinds of system data and has this Oracle root cause knowledge from the PRPs. So that would be like our kind of future step which you were talking about.
Thanks, Amrita, for your answer. So we have another question for Manish. So how do you collect the level of data in the transfer learning?
Yeah, thanks for the question, Z. Yeah, so like I said, the label data comes from Bang Analyze itself. So like I said, this is a tool that we believe in, we trust in, and we've been using for a while. So we get that it's basically almost like a week supervised data, but then the supervision is quite very accurate. So we just use that as the ground truth in our analysis, every analysis.
Yes, thanks.
Okay, thanks. So actually, I have a question for Hong. So according to your slides, I was impressed about the fact that in a way, developers close, warning accidentally, or, they're really not aware about, the presence of a warning. So I think that it can be really interesting to, understand the perception of developer, maybe using survey or, focus group, in order to, I think, that reinforce this study that is already really good. And so comment in principle, but I have a question, important question. How far are we at the end?
So, well, we're not far. We're far from solving the problem entirely, but there's certainly progress that's been made. So, as I said in the presentation, the features that we used they were predictive. They had AUC greater than 0.5, so they were not entirely random, and we were getting numbers that were generally positive, although it's not as high as the prior work. So another thing to point out that I missed out in the presentation was that when we clean up the data when we experimented on the manually labeled data, we actually had a slight performance improvement. So it does indicate that it's very likely that the performance that we see now is actually would be lower than what we would had if we had labeled a lot more data, or we had some way to deal with the lack of data. So it's likely that we could push the performance using more sophisticated techniques like newer machine learning models, pre-processing techniques. So I can't exactly say how far are we, but there is progress, I think.
Yeah. Okay. Thanks. Yeah, I think that. Okay, I don't see any other question, but actually I have also a question common for Zhu-san. So if I correctly understood, you apply your approach for English and Chinese language, right?
Yeah.
For example, during your presentation, I told also about not only about words that were wrongly translated, but also to the fairness on how this kind of word can be translated. And for example, in the context of fairness, I think that in Italian, in a way, we have the same problem of fairness. I mean, do you plan in future work to also consider to apply your approach for different languages, but also consider to investigate in the fairness? So when we talk about translation of languages.
Yeah. I think our approach can be applied to many different languages, and we only do the experiment in English and Chinese, but I think it can be worked on many different languages.
Okay, Thank you. So
Thank
we
you.
have 30 seconds before our session ends. I hope that you enjoy the session. Me too, for sure. So I would like to thank again our presenters for today for this session about machine learning. So see you around in the mid-space area environment, and hope you again enjoy the session. So an applause for all the speakers and presenters here. Yeah, so see you around.
Thank you. See you.